Welcome to our sixth learning workshop over acid-base equilibrium for Chemistry 1412. Let's go ahead and get into this. So for the first problem, it says which species below is the strongest base, and our esteemed leader, Dr. Neely, is going to go ahead and take us into this.
Hi. So our first problem is looking into figuring out what's the strongest base. And really what we have to look back into is to what is the relationship between a strong base, a weak acid, or vice versa, a weak acid and strong base. So in our first question, we have a series of bases and we have their dissociation constants with the correlating conjugate acid. So Victoria, if you would please tell us out of the 5 choices for hypochlorite, nitrite, cyanide, and chlorine, or none of the above, which one is the strongest base?
Okay, so for me, if I recall correctly, depending on the value of Ka given here, sorry about this. The weaker the acid, the stronger the base. So for me, the fact that the Ka of cyanide's conjugate acid, which would be like hydrocyanic acid, if I'm right,
Yes.
it is the smallest. So for me, I'm assuming it's going to be C.
Yes.
Yay! The reason why we're not provided the Ka for hydrochloric acid is because hydrochloric acid is one of your strong acids, so we don't have to like worry about that. Which means that this the base Cl minus is going to be like really weak compared to the other bases.
Yeah, it's going to be so incredibly weak that it effectively has no real basicity, no real power to abstract the hydrogen.
Yes.
So yeah, you're absolutely right, and it's just that basic that I don't want to use the word basic, but it's that simple rule that the stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. So
yes, and it is true that we have not indicated the Ka in there, but if we were to numerically put a Ka there, would you expect it to be quite small or quite large?
For the chlorine atom, is what you're saying?
Yes.
I would expect it to be a very large.
Yes. Great job. I think we're all on the same page on this problem. Good job.
should we jump back to
2.
number 2? Yeah, there you go.
Yes.
Associate the following acids. Oh, do you want me to write this down, like, and then say it, or?
Please.
Yes.
You can even write it down right on the paper, because you can actually write right on here.
Oh, that's right. I can also type it in.
Yeah, you can definitely do that as well.
Let me see if I can do. Okay, so for the first one, I would say, can everyone see my little letters?
I can't see anything, but we won't be able to see it if you're typing it in until you hit enter.
Yes.
Oh, okay. I apologize about that. Let me go ahead and get this through. See, so So for hydrochloric acid, I got the following here. Can everyone see
Yep,
my answer?
we got it.
Yes.
And
Awesome.
just
Okay.
alternatively, I just wanted to demonstrate the Bronsted-Lowry representation as well after you do it,
Mhm.
because Bronsted-Lowry proton donor proton acceptor, this is more accurately reflective of what happens on the molecular level when these acids are introduced into water. They react with water to form H3O plus and then the conjugate base, in this case Cl minus.
I see. Do you want me to
Oh no, go ahead,
Yeah,
just
yeah,
execute?
dissociate them the normal way,
yeah.
and then I'll go
On
ahead
this
and
problem,
go
yes,
ahead.
on this first problem, because the complete chemical reaction has been written, can you please identify which one is the can you identify the Lewis acid base pairs? I guess is what I'm after.
Lewis acid base pairs.
Yes. Or conjugate
For
acid
A.
base pairs. Uh-huh.
Oh, okay. Conjugate acid base pairs.
Yes.
For the one that I
Okay.
wrote,
Yes.
Okay. Um, I'm gonna label these in orange. So let me just make sure. I realized I did not put down the little
that's
snippers.
that's totally fine. And to be honest, it's probably more appropriate to use Bronsted-Lowry acids and Bronsted-Lowry bases
Oh
because
shoot!
it
I must
Oh,
it
good.
apologize.
no no that
I
is
got my
appropriate.
text mixed up.
That is appropriate because the Lewis, we don't really deal much with I mean we don't really deal much with the designation Lewis acid and Lewis base
Right.
in Gen Chem 2, but we definitely will deal with it more in organic chemistry. But
Uh-huh.
you're absolutely right. Very good. Well done.
Good job.
Thank you.
Yeah, the acid and base are always the acid and base are always your reactants, and the conjugates
Mhm.
are always your products. So what would be your conjugate acid and conjugate base here?
Oh, sorry.
There you go.
Acid. I must apologize like if my spelling's a bit off.
No, your
No, I,
spelling is perfect actually. So great job.
Awesome.
Absolutely.
Okay. I'm pretty sure this is
wow.
it.
Nice.
Yeah, excellent.
Thanks.
And so go ahead and do the simple dissociation with the H2 or the acetic acid, and I'll go
Mhm.
ahead and follow you up with the reaction with water.
Okay. So, so again, I'm pretty sure it would be very similar to what or to what I was able to do with hydrochloric acid. The only difference is that in terms of the Bronston-Lowry representation, it's only going to be a partial dissociation, which means that we will have both the reactants and products in dynamic equilibrium with each other.
Very good.
Yes.
Thank you.
So what would be the ion that's the? There you go. You got it.
Uh,
Okay.
what would be the ion?
Oh yeah, you already put it, so you're fine. C2H3O2 minus.
Mhm.
Very good. Now, what
Yes.
about the third one? C is just a little bit different.
Oh, okay. That looks like one of your memes. This is this looks like to be the conjugate acid of one of your amines, which is a weak base.
Yeah, one of your nitrogenous bases. Yep.
Mhm.
Yes.
Again, I apologize. I can't do what is it? Subscripts or superscripts on
No,
here.
that's totally fine. Totally fine.
And actually, I do like the way Professor Depart is writing the whole chemical reaction because you do need that water molecule, that's your bulk medium. So it is chemically correct to do that. Thank you, Professor DePaul.
Oh, my pleasure.
It feels silly. It's acting as an acid, so it's going to be. I was in the like mindset that it's base, so I got confused for a second.
Oh, sure. Yeah, very good. You took the hydrogen from the right spot. That's good.
If I
C6.
recall
Yes.
correctly, I think this is crud. I think this is aniline.
Aniline. Very good. Exactly what it is.
Awesome. Oh, that
You're
makes me
organic.
happy.
You're set up for organic chemistry.
Oh, that makes
Indeed.
me
That's.
so happy to hear.
What is your major? What are you studying, Victoria?
Oh, actually, my major is a bachelor's in chemistry.
Oh, good.
Oh,
Yes.
wow.
What a coincidence.
Very nice.
Yeah, you have.
I'm
Yeah, you
actually,
definitely have the skills for it. I mean, I've always been
thank you.
Yes.
impressed with your level of knowledge coming into these sessions. So,
Thank you.
Yes.
Um, I'm actually like, sorry. The other day, I found out this type of like particular field of chemistry called organometallic chemistry.
oh yeah.
So I'm like,
Hmm.
oh, I'm I'm trying to like I'm trying to find like potential careers within that field,
Well,
even
I
though it's
can.
kind of brand new.
No, it's not new. Organometallic chemistry has been around for a long time. However,
Oh.
I can tell you that as far as marketability, if you pursue a PhD in polymer chemistry, it
Hmm.
is organic slash polymer chemistry. It is very marketable.
Ah, I see.
So we
Okay.
can talk. Yeah, we can at some point whenever you want. Both Professor Depa and I can talk to you about that whenever you're interested.
Hmm.
Oh, yes. Thank you very much. I didn't know that. Sorry. I'm still new, like to like the whole job searching. Oh,
Oh yes,
Oh
yes.
yeah. Yeah. Okay, so what do we get for this last one? This is probably the hardest one to do.
oh yes. I'm pretty sure this is a complex ion from the hydration of the aluminum cation. The formula's a little bit formula's a
Messy,
little bit
messy.
foggy in my head, but
Right.
if I recall correctly, I'm pretty
It
sure.
is a little bit confusing. Um, hmm.
I know that it is producing a hydronium ion, so crud. I actually can't say it off the top of my head. I apologize.
That's okay. I can't either.
Oh, that makes me
Yeah,
happy to hear.
that's a hard one. I'm thinking about it.
I have my text open. It's around here. Oh, I think I found it. Um,
It's like aluminum
uh,
hydroxy pentahydrate.
it would be Al and then in parentheses H2O. The subscript for the H2O is 5, and then it is in
Yep.
parentheses OH to positive 2, 2 plus for aqueous plus the hydronium ion.
Yeah, and
That
sometimes they
is,
like to. Yeah, sometimes
oh,
they like
sorry.
to. Oh no, I was just gonna say sometimes they like to go ahead and have you put it in brackets and then do like
Exactly.
the charge outside of it, 2 plus. Hmm. And then plus, of course, H3O plus.
Uh-huh. Interesting. That's a tricky one there. That's Okay,
I thought you were
so
talking about the name, and I was like, if I had to guess at a name for that ion for that complex ion, I would say it's aluminum pentahydroxy, or it's aluminum hydroxy pentahydrate, but I don't know.
sounds pretty good to me. I cannot come up with a different one.
Your guess is as good as mine.
Hydroxy aluminum pentahydroxide. Yes, I like it.
All right, so are we all good for moving from there?
Yes, I'm good here.
Yeah,
Yes.
the key thing with those is that, and sometimes they'll represent these more simply. Sometimes they'll just say, okay, well, we want you to, if you want to do like a simple representation, which is sometimes what they have you do, they'll just say, okay, well, you can take the Al3 plus, and you can say, well, it reacts with the H2O, and what it does is abstracts, it abstracts an hydroxide, leaving the H plus behind, so you end up getting ALOH with a 2 plus charge and a complex ion, and then you get the remaining H plus by itself. That's not really accurate to what happens. The
But
above
actually,
equation is certainly
it,
better.
it really makes sense. I mean, you know, when you simplify it like that, the ionic equation makes a lot of sense. So
Mhm.
if there is a confusion in figuring it out, that's a very nice trick to move forward. I like it.
Yeah, and it kind of gives you an idea because I mean a lot of those waters, as you can see up there, they don't really change anything. They don't really do anything. They just kind of sit there attached to the aluminum. So this kind of filters out some of that noise, so to speak, and you can actually see what's kind of going on there. Um,
Yes.
yeah, no, that's great. That's great. And because in this case, the aluminum ion itself is really not a Bronsted-Lowry acid. That's the thing. So you couldn't really do the Bronsted-Lowry acid, Bronsted-Lowry base pair here. I mean, I guess you could kind of make an argument for it with the complex water molecules, but
Uh-huh.
in essence, the ion really is, these metal ions are really Lewis acids. They really can't be classified as, um, they really can't be classified as Bronsted-Lowry acids. These are Lewis acids, and water, and then since it, well, actually, and water, the electron pair acceptors, the Lewis acids are, and
Yes.
water here ends up being the electron pair donor or the Lewis base.
Yes, 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 because Lewis acids and bases by definition is based on electron pair donation and acceptance. That is correct.
Exactly. Does that make sense?
Yes.
All right, cool. All right, let's.
Yes.
Are you ready to dive forward then?
Oh, and also just to like be sure of the ALOH 2 plus that would be the adduct, correct? Or am I off?
That would be a what?
The adduct, the Lewis adduct.
Oh, I yeah, I guess you could think of it like that. Um, I like. I was trying to think about whether or not the word adduct could properly be applied to that particular situation, but I
How
think
do you spell that term? And because I'm not
Uh,
understanding.
no,
uh,
you're fine.
I think it could. I think it could be applied to that term. It's adduct. Yeah.
Adduct. Huh.
So
Not
you'll
that I
sometimes.
know of.
Yeah. Like so. Like for example, with the where the only other place that I know of where that term has come up, where I hear it commonly, is when we were talking about the combination of molecules that comes from a Diels-Alder reaction. We'll call it the Diels-Alder adduct.
Oh, okay.
Aha. There's the organic chemistry expert for us. Thank you. Thank you.
I have to uh, um I have to apologize like for the confusion. It's just that according to the book, I have it right here. I always refer like to the text.
Oh, sure. No, that's good. Yeah. No, I think adult could be referring to could refer to any situation where you have a combination of things come together in a
It
chemical
just
reaction.
says that. Oh, sorry.
Go
It
ahead.
just
Go ahead.
says that it just says that the product of a Lewis acid-base reaction is sometimes called an adduct. So I'm like, oh well, I think that's what it is potentially.
Yeah, because that's when you have the two things coming together. Because a lot of times with the and Lewis acid Lewis base reaction, it'll result in a coming together of two particles or two. Um, I don't want to say molecules because they're not always molecules. Sometimes it's an ion and a molecule or whatever. But yeah, you're right. Yeah, I think that works.
I
All
see.
right, cool.
Yes.
Okay.
So now let's take a look at this. This is Kw is 1 times 10 to the negative 13th at 60 degrees Celsius. Notice it was 1 times 10 to the negative 14th at 25 degrees Celsius.
Yes.
So using the Chatelier's principle, predict whether the H2O going to form H plus and OH minus is endothermic or exothermic.
Okay. Mhm. Excuse me. Let's see. The problem is that for me, I don't know whether or not heat is. I must apologize. It's just I don't have enough
Oh
like
no.
information regarding the formula to know if it's endothermic or exothermic.
Oh well, actually, that's what the KW is supposed to tell you. So this is not an
Ah,
obvious one, but if you understand that KW is equal to 1 times 10 to the negative 14th at 25 degrees Celsius, and it's 1 times 10 to the negative 13th at 60 degrees Celsius, at what temperature is it a higher value of K?
oh, at 60 degrees Celsius.
Yeah, so if what's and so the difference between 25 and 60 degrees Celsius is that at 60 degrees Celsius you've added heat, haven't you?
Oh, so it's endothermic.
Yes.
Yeah, yeah,
Okay,
exactly.
Yes.
So
I
it's
didn't.
endothermic. If you add heat and it shifts if it add heat and it shifts the equilibrium towards the products, then yes, that is a sign that it would be an endothermic reaction because if that means if I had like if I wrote this reaction with heat in it, I'd say like heat plus water gives you the other. So if I add heat, yes, that's going to shift the whole thing over to the
Okay,
product side.
let's see. Okay. Plus, it makes sense in a way, albeit it's going to be a lot of heat. You need to like apply like some sort of like energy
Yes.
to separate the hydrogen and the hydroxide ions. Okay. I
Yeah.
apologize.
It,
I didn't
no,
come
no,
across
you're good.
something like this.
Yeah, you don't have to apologize. Yeah, no, it's good that that you sometimes are hit with questions like this that make you think. The truth of the matter is, the major difference between equilibrium problems that deal with heat is that heat, although it can, if you can look at it in terms of the reaction, it does follow the same Le Chatelier's principle. Like if heat is a reactant and you add heat, it's going to shift it towards products, or if heat is a product and you add heat, it'll shift towards reactants. However, the key thing that is how does that happen? Well, it doesn't happen by altering the concentrations of anything, so it must happen by changing the equilibrium constant. And that's the thing that gets students so messed up, is that when you change the temperature, you actually change the equilibrium constant. And you change it based on whether or not heat is, the reaction's endothermic or exothermic. In other words, whether or not it absorbs heat or releases heat.
Ah, okay.
Yeah, and also it would have been better to start the problem with, given that at 25 degrees Celsius, Kw is 10 times 10 to the minus 14, then predict what happens, etc. So yes, I'm
I kind
making
of like
it.
it the way it is though, because I mean,
Uh-huh.
the one of the like I hear what you're saying, like that when that information's not given, it kind of doesn't give you a lot to go from. But
Right.
one of the one of the things that you'll notice, especially in higher level chemistry courses, like when I was taking physical chemistry, they would not give you anything, like any
Yeah.
sort of extra information like that.
Yes.
So you had to basically kind of figure out a complex series of things, and a lot of times you end up having to look stuff up in like reference books and things like that.
True.
But the reason that they do this because in most cases, like when you're an actual chemist, it's not that things are just going to be given to you. Most things you're going to have to have kind of an intuition built on your knowledge base that certain things are related. And when you're approaching a problem, you'll be like, okay, well, how can I figure out this information? What information do I need to kind of like figure this out? And how can I potentially, do such and such and such? And then you can do the research, pull up the information that you need, make use of those relationships that you know, and then come up with a solution.
So then this is a very good pedagogical example, especially because Victoria is going to pursue chemistry.
Yeah, absolutely, absolutely. It's good for critical thinking too, just in general. Um,
Also, not to sorry, also like not to mention, my prof of also make sure to remind us to to memorize specific like formulas and also some values, such as the KW specified above. So
Oh, so
oh,
so
okay,
you,
cool.
okay, so good. So it's so you have been asked to memorize some standard data such as the KW of water at standard temperature.
yes.
Mhm.
Uh-huh.
So for me, so for what Mr. DePaul said,
Depart.
I understand like where he's coming from.
Mhm.
Uh-huh. Very good. Thank you. Thank you for elaboration.
Just thought I clarify that.
Thank you.
And for part B, there would need to be just a little bit of extra information here, but I think the question is asking
Yes.
find OH in a neutral solution.
Yes.
The moment that you said uh, a neutral, this is for the 1 times 10 to the power negative 13, correct?
Yes, exactly.
Yes.
Neutral solution of water at 60 degrees Celsius. I probably should have
Yes.
added
The
that. Yeah.
neutral solution that or the value that I got, since it's 1 sig, it's going to be 3 times 10 to the power negative 7 molar concentration for the
Excellent.
hydroxide one, as well as for the high hydronium ion. Because if the solution is neutral, their concentrations should should be the same.
Awesome.
Yes.
Thank,
Absolutely. You're 100% correct. Very
thank you.
good.
I was able
All right.
to find. Oh, sorry.
No, go ahead.
For, for those that are watching, I was able to find the concentration by finding the square root of the new KW value.
Yeah,
Aha.
because this is all basically on the autoionization equilibrium of water, which is basically one water molecule. Um, and this is just one way to write it. You can also write it other ways, but one water molecule is in equilibrium with H plus and OH minus, as shown above. And then, of course, not necessary to do this if you can kind of see it, but it may help to draw an ice chart.
Aha.
And then if you draw an ice chart, trying to make the line as straight as possible. Okay, you initially start out with 0 of this before the water begins to dissociate. Remember, that's what the initial means. Before the reaction begins to happen, before the water begins to dissociate, you have 0 H plus and OH minus. However, um, then it dissociates, and of course, that means a certain amount of this breaks up. We don't actually care because it's a liquid,
Right.
We don't actually care about the concentration because the concentration is based on the density of water. And so that's not going to change. But we do care about the fact that the H plus is going to be a plus X. Plus X. And so then
Yes.
essentially our equilibrium values are X and X. And so if I have H plus, and I'll actually just do the simpler form of this. I'm going to drop that 3. I was going to do the hydronium, but I'm not going to do that. And that, so Kw is going to be equal to OH minus times H plus. And then if I just go ahead and substitute the X, so basically it's X squared is equal to Kw. And that's why Victoria just went ahead and took the square root of that.
I am convinced that you have a magic pen because otherwise nobody can write so well on this platform. You have a special magic pen that you're not going to tell us about.
I'll prove it to you at some point. I'll prove it to you at some point. So yeah, 3 times 10 to the negative 7. Excellent job.
Yes.
There we go. Cool.
Thank you.
All right, now it says find the pH of a solution with the OH concentration of 1.7 times 10 to the negative 5th.
Oh, so for me, I'm going to assume that the solution is at 25 degrees Celsius.
Okay, absolutely. That's a good point. That we really need to know what the solution temperature is. In this case, it's 25 degrees Celsius. That means that it's 1.0. I think it's 1.00. I think we can give 3 sig figs times 10 to the negative 14. It might not be. I think it might only be 2 sig figs, but oh well. Actually, I'm just going to say 2 sig figs.
Yep. For me, it was 2 sig figs.
Okay.
So for me, I was able to calculate this within 2 steps using the formula. If you don't mind me typing it down, Kw equals hydronium ion concentration times the hydroxide ion concentration. Give me a second. I need to type it down. Make sure it's 3O plus. I just basically solved for the hydronium concentration by dividing 1.0 times 10 to the power negative 14 with 1.7 times 10 to the power of negative 5. And then the next formula that you're going to use to find your pH is pH equals negative log of the hydronium concentration, which will be, give me a second, which will be this formula, in which what I got was let's see, with the number of sig figs, it'll be 2. So my reported value for pH is 9.23. For in terms of sig figs,
Very good, very good. Yeah, because so I think I know what you're going to say, but yeah, the significant figures of a logarithmic value are the number of places past the decimal point. So absolutely,
yes.
very good.
Yes.
Yeah, and that's because the first number, the numbers before the decimal point indicate the power. So that's why even if it was like 12 point something, it would be like 12.24. You'd still have to do 2 places past the decimal because it is the um, number of places past the decimal that indicates the sig figs of a logarithmic value.
I see.
One of those odd, it's one of those odd,
Yes.
strange rules for
Yes.
significant figures that we
Yes.
don't really actually explain too often.
Right,
It's
but
okay. It's fine.
yeah, I'm impressed by how quickly you were able to do that. That's excellent.
Very cool. Yeah, very cool. Good
Thank
job.
you. Thank you.
And so now, I don't know, 5 is probably pretty simple. I don't think we probably need to go over that one. That would just be like
Yes.
1 times 10 to the negative 7, and therefore the PaOH and the pH would just be 7. So that's just a neutral, pure water thing.
Agreed.
Yes. Mhm.
All right, so let's skip that. pH of a sample, 7.41. This is, for some reason, this is something that students just kind of, even though it's a relatively simple problem, oftentimes make a mistake with it. So how do you revert pH, and how would you get that to OH minus?
Oh, okay. So for me, um, um, I just basically work backwards with the same formula. If you don't mind me, I'll just type it down again for those that are watching. Mm,
There is no for me in science. There's only for science. No, I was kidding.
Uh, so for me, I got the pH, I got the high, I got the hydronium ion concentration by calculating 10 to the power of negative 4.71. I got 3.9 times 10 to the power of negative 8 as your concentration.
Mm-hmm.
And, and then with the KW formula specified before, I just basically divided 10 to the 1.0 times 10 to the power of negative 14, or, uh, or just simply 10 to the power of negative 14, which are calculated hydronium
So, so,
ion
so did you take
concentration. And
did
all.
you actually solve for the hydronium concentration first by taking 10 to the negative pH is equal to H0 plus?
Uh, yes.
Okay.
Okay.
And that's definitely one
And
way you could have done it, and then you follow it up with the KW formula. KW is equal to H0 plus times OH minus, right?
yes. And for me, I got a 2.6 times 10 into the power of a negative 7 molars for the high hydronium concentration. Another way to solve this is also solve for POH,
Yeah.
then find the hydronium ion concentration right then and there. But the
And,
formula POH equals negative log of the hydronium concentration.
yeah. And honestly, that would have been my preferred way to do it, just because I don't
And
know
that's
why.
the way I was, yes. And actually, in fact, I started to doing it like that, and I'm almost down to my response, and I get 2.6 times 10 to the minus 7 molar
Very
using,
good.
using the second track, using POH is equal to 14 minus pH. But yes, both ways, yes.
Excellent.
Good job. And
Now,
let's skip 7. Let's
oh
skip
no,
7.
problem number 7 is mean.
Oh, let's see.
You have it.
Fine.
Yeah, problem number
pH.
7 is mean. That is a tricky one. Like, yeah, this is a tricky one. This is a tricky one. This is a problem that you might expect to be easy, but this is actually a problem they throw at you in analytical chemistry. Um, so if you were
Uh-huh.
if you were to think, oh, I'm just going to go ahead and take the negative log of 1 times 10 to the negative 10th. No, can't do that. Because this 10 to
Mm.
the negative 10th, if you took the negative log of that, you'd get a pH of 10. Well, how can a solution that has acid in it be basic? It can't, right?
Oh, right. I would assume so.
So yeah, so you can't have an acid solution that ends up with a basic pH. What you have to recognize is that as soon as the HCl hits the water, it turns into H plus. Okay,
Mhm.
so this is what you end up having to do. I hope you don't mind me kind of jumping into this, because this is not something that you would necessarily know how to do offhand.
Yeah,
You
it's
act,
kind of
Oh, no,
tricky.
no,
You're
that's
right.
fine.
so this is what you end up having to do. And I'll just use the simpler Arrhenius form rather than the Blanchard-Lowry. But essentially, you would have to use the autoionization of water. It's H plus OH minus. Okay? And so what you would end up having to do here is this. You would have to, once again, this is a liquid, so concentration, we're not going to worry about that, but that's going to be minus X. But the initial concentration but the H plus is not 0 here because of that 1 times 10 to the negative 10th molar HCl. The initial concentration is 1 times 10 to the 10th, times 10 to the negative 10th. And the initial concentration of hydroxides is 0. So this is going to be plus X, and this is going to be plus X. And so you end up with 1.0 times 10 to the 10th times 10 to the negative 10th plus X. And then you have to do the quadratic equation. Because, of course, it's going to be essentially KW. You're going to use the KW equation, right?
Sure.
Yes.
Equals. Well, I already have it written above, so I'm just going to go ahead and put in the numbers. So 1.0 times 10 to the negative 14th is equal to X. Well, it's equal to 1.0 times 10 to the negative 10th plus X times X. Does that make sense?
Yes.
And so then at this point, it's up to you if you want to kind of dive into this and do the quadratic equation, but effectively you're going to distribute that X across this, multiply times that, right? And that's going to give you
Yes.
X squared plus 1 times 10 to the negative 10th X. And then you'll have to pull the 1 times 10 to the negative 14th over by subtracting it from both sides, set it equal to 0, and use the quadratic equation.
Let's see. Do you want me to solve this right here, or
Or if
sorry,
you
if
know,
it's obvious.
yeah, sure. I mean, it's going to be a little bit time consuming. So if you,
Yeah.
So we could skip the actual solving part, but if you understand like how to proceed from here,
right.
yeah,
Yes.
yeah. So I would say it depends on how evil your professor is, but if you get a
Oh my goodness.
if you get a low concentration of an acid, like I'm talking about, really anything, yeah,
Oh,
really anything 10 to the negative 6 or smaller
Yes,
concentration of
that's a
acid,
good break
you might
off.
actually end up having to do this because, yeah,
I see. Oh, okay. I just recognize what is going on here. Um, 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 Apologies. Ooh, I stutter so much. Um,
No, you're
no,
good.
it's
You're
okay.
good.
um, uh,
So do I. So do I.
uh, it's because of it's because for me, I was just simply simply like taught to like taught to like convert the moles of HCl to moles of the hydrogenium ion for strong acids of them. But this
Yeah,
is like a really dilute uh, uh,
strong acid.
uh,
Exactly.
strong acids. So I'm like, oh, I see why we're like taking like this like alternate approach.
Yeah, because
Correct.
there's an equilibrium here, and usually the strong acid, because the strong acid does completely dissociate. Usually, the strong acid is such a huge factor that the any amount that would be added to give the hydroxide its appropriate amount would be negligible. Like for example, if I had 1 molar or even point 1 molar acid, um, it would start with point 0.1 molar and then add x to both sides. Well, you'd end up adding 1 times 10 to the negative 13th to both sides. So basically, if it was point 0.1 molar plus 1 times 10 to the negative 13th, well, point 0.1 molar plus 1 times 10 to the negative 13th is pretty minimal. And likewise,
Exactly.
even if it was like 0.001, well then 0.001, you'd end up adding 1 times 10 to the negative uh, 11th to both sides. And so, but once you get close, and then after that adds to both sides, then you have to uh, adjust equilibrium values. Like it's gonna shift in such a way as to balance out for equilibrium. So it's not actually a perfect 1 times 10 to the negative 11th or 1 times 10 to the negative 13th that gets added. But it's so close, and that amount is so small that it doesn't really matter when the concentration is decently large. However, once you start getting down to 1.1 times 10 to the negative 6 or 1 times 10 to the negative 7,
Hmm.
then it's like, ooh, well, 1 times 10 to the
Yikes.
negative 7th is what it has at neutral? So that's where
Mhm.
it starts getting a little bit mm, not so sure?
Yes. So really, just based on that comment, if I wanted to take the lazy way out, I could say the amount of hydrochloric acid is so small that really it doesn't have any effect because the major species is just going to be water. So I can pretty much assume that the pH is just going to stay at 7.
Well, that's in this case that you'll find that it's not quite the case. I mean, it will be noticeably different, but just
Uh-huh.
not a super amount. You're right. It is probably going to be close to about 7. It is probably going to be
Yes,
close to
right.
about 7.
Because like you said, this concentration, even though it's a strong acid, it's 3 orders of magnitude smaller than the concentration of the hydronium ion,
That's a
in
good point.
solution.
That's a good point. That's a good point. Yeah, it would probably be like 6.97 or something like that.
Uh-huh,
Probably
uh-huh.
something really tiny.
Uh-huh.
But yeah,
So again, it's going to depend on the teacher. If they want to be wicked, they'll say show your work, or if it's a multiple choice and there's a few that are conspicuously differing from each other, then I would just say I'll just not do this problem quantitatively. It can be laborious and tricky. I'll just qualitatively evaluate it and say, yeah, pH is close to 7 and I'm good to go.
yeah.
Yeah,
And if you're
actually,
given a multiple choice question, then and you see the answers like pH is 10, pH is uh,
Yes,
2 or something like that, and
yes,
pH of 4, and then like pH of 7, be like, oh yeah, pH 7, got it.
exactly, exactly.
I understand. Um, I guess, or oops, sorry. It's just that I haven't like seen like seen these like types of problems where there are exceptions. So this was nice to see, just in case.
Yeah, yeah, I'm glad Professor Depot caught that this is a wicked one.
It
We
is.
kind
Ooh.
of we use teamwork to solve it.
Yeah, there you go. There you go. And that's a good observation that you had, though, Dr. Neely, on the fact that the order of magnitude is so small, it probably would be kind of a minimal change. But no,
Thank
that's good,
you.
yeah. Well, cool.
Thanks.
Let's go ahead and see what else we got. Uh-huh. The 0.12 molar solution of nicotinic acid has a pH of 3.39. Find the Ka. Ooh, this is a good one. How would you start a problem like this?
Let's see. So for me, we are given we can infer or sorry, based on my list of strong and weak acids from my memory, even though it wasn't specified, I can assume that that nicotinic acid is a weak acid, meaning it is
Yep.
going to partially ionize, which means that I'm going to have to find specific differences within the changes of the equilibrium concentration and the initial concentration, but I can be able to figure out my magnitude of change from the pH by finding the hydronium concentration. And then by applying the stoichiometric ratios, which we would assume from the formula of the ionization of the nicotinic acid, we will find our respective equilibrium concentrations for both the or for both the reactants and products, and then we can find Ka there on out.
Yeah. So like to put in, I mean, first thing that I would recommend honestly is to write a reaction equation, write the
Yes.
chemical equation. And specifically, I prefer to recommend doing the Bronsted-Lowry version of these Ka and Kb reactions because like and with Kb reactions sometimes you don't really have the choice. But I always say Ka and Kb reactions are reactions with water. So I'm going to take this whole HC6 H4 NO2 and I'm going to react it with water. And what will be the products of that?
Uh, it would be the hydronium ion and the
Uh-huh.
conjugate base of the nicotinic acid, which would be C6H4NO2 minus.
Yes.
Uh-huh. There you go. Bam. So then we do ice chart, ICE. So what did the doctor say to the patient who came in with a headache from doing chemistry problems?
I have no clue. What did they say?
Said, ice it and call me in the morning. Oh,
Okay, say it again. I couldn't catch
I
it.
couldn't
Could
hear
you?
you.
the
Could
pa- the
could you?
pa- the pa- the patient came into the doctor and he's like, "Oh man, I have this huge headache. I was doing all these equilibrium problems in chemistry.
Uh-huh.
Can you give me
Yes.
something?" He said, "Ice it and call me in the morning."
Oh my God.
Okay, so I guess I'm not hearing it too well. I got the first part and then the second part. Something call me in the morning.
Oh, ice it and call me in the morning. It,
God.
it's a really lame chemistry joke. Sorry, really lame
That
chemistry
that
joke.
is funny. That is funny. Good one.
I'm a sucker for like a lame joke, so we're good. We're good.
It's almost as bad as like, are pH problems hard? No, they're pretty basic. Yeah, yeah. Sorry.
That's
Anyway, shame on
funny.
me. I need to stop or I'm gonna get hit with something.
You're
That's
Okay.
too
fine. You're
funny.
fine, man.
All right. So with the acid, it tells us the initial concentration is what?
0.12 molar.
Yeah. And on the other side, what are the initial concentrations of H3O plus and C6H4NO2?
0 for both.
Okay. Now, technically, that's not correct. That H3O plus would actually be 1 times 10 to the negative 7, but it's close enough to 0 that we can put 0,
Yes.
Yes.
especially with this pH being what it is.
If you don't mind me, like also like writing down this as well, in terms of my or whenever I would do these types of problems, to remind me that that there is like technically a small amount of the hydronium like concentration but but we
I'll
are
put a
able
little
to like
asterisk down here.
estimate it at 0. I just write down this little like approximation symbol.
Ah, oh, yeah, okay, good call. I was going to write a little
Sure.
asterisk and type, but no, that's
That's
perfect.
yes.
That's perfect. That's
Close enough.
actually really smart. That's really smart. Okay.
Yes, I like
There
that.
we go. All right, cool.
Oh,
And then, oh, go ahead.
sorry.
You want to take it from
Then
here?
for the if it's not a problem, yes. And then from the pH, you can be able to infer the the, uh, the, the equilibrium concentration, which for the hydronium ion, which for me, I according to SigFix, I got 4.1 times 10 to the power of -4 here,
Uh-huh.
and then
And one thing I might even recommend is even to just write this, do the whole, I know this is going to be a minus x and this has to be a plus x, right?
yes.
And so therefore the fact that the H3O plus ends up being 4.1 times 10 to the negative fourth, that's x, which means that
Yes.
Right.
yeah, the others, it means you can calculate each of these other three values. And then, now of course, the 4.1 times 10 to the negative fourth subtracted from 0.12 is not going to really do anything, right?
Yeah.
Right.
So you can then just go ahead and set up the Ka expression, plug in the numbers, and solve. Very good.
Yes.
Thanks.
Dang, Victoria, you have this down. You have
Yes.
this down.
That's very sweet of y'all. Thank you. However, though, I'm kind of nervous on how like I didn't understand a couple of the like earlier problems. I didn't come across like something like that when I was practicing.
Yeah, I think one thing you need to be careful of is that a lot of times students get so hung up uh, on the workout problems, like the calculation problems, they
Hmm.
don't spend enough time really taking the time to
Get the
go through the
concept.
definitions and the
Yeah.
concepts.
Yeah.
And there's a lot of concept and definition problems that professors like to toss onto the tests. Especially at TCC, I've noticed that there's a lot. Usually, with most of our professors, you can expect at least about half of the problems to be mainly concept problems and not
Conceptual.
calculation problems. Yeah.
Ah, I see. I got you. Uh, 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 Um, it's that again. I remember reading about the more. Sorry, I remember reading about the about the exceptions with the more dilute solutions, but it didn't go in. It didn't go any deeper than that. So I was like, oh, wait a minute, there it is.
Gotcha. That makes sense.
Oh, so for Ka, I got 1.4 times 10 to the power of -6.
You're
Sounds
quicker
good to
than I
me.
am. I
Oh,
just punched out the number and hold on for it.
Wait for it. Wait for it.
1.4 times 10 to the -6.
There you
Yay.
go.
Our answers
Awesome.
agree.
you.
Y'all are champions. That's awesome. All right.
Think,
Shall we proceed to the next?
yep, I'm good.
All right. Let's calculate the pH and concentration of all species for a 1 molar solution of acetic acid.
Oh, okay.
So you may or may not need to do this, but one of the things that I especially recommend with students who are just starting with this equilibrium stuff, write out the equation first. Um, and for acetic acid, you don't actually have to write, and actually for most weak acids, I'm usually lazy and I don't even bother write the full formula. I
I
just
like
write the
that.
generic weak acid formula. It's just H.
Saves time, saves time.
It's fine.
It's a good cheating technique.
Absolutely. HCl plus, bam. And OH. No, not OH minus. What am I doing? My brain is not here today completely. All right, A minus. There we go.
Don't worry, we all have brain farts every now and then.
Mm-hmm. All right. There you go. I leave it to you, my esteemed student and colleague. Yeah.
Okay, Victoria, since you're quicker than I am, you get to take the lead.
Yes, ma'am. Okay, so basically, it's very similar to what we did earlier. However, though, this time we're going to have to find our equilibrium concentrations and then use one of our equilibrium concentrations to find pH. So it's kind of like backwards to what we did last time. Uh, can you guys hear me?
Yes.
Okay, sorry. I thought my mic was off. Okay. Okay, so for obvious reasons, or not obvious reasons, I must apologize. Um, so because water is a liquid, we won't have to worry about its concentration here. So you could
Yes.
just specify the little red lines there. Um, um, as for just to make this a little bit easier to start off on, we can specify our we could we'll specify our initial concentration of HA here, or just simply acetic acid. And then we can assume, technically because of autoionization, there is a little bit, but we will assume approximate 0,
Yes.
and then also 0 here for the conjugate acid solution for now. In terms of constant, in terms of equilibrium concentrations, we will apply changes in the form of x. So over here, because we are decreasing and because we have to go in the forward direction to have some form of product, the amount of reactant will decrease and the amount of products will increase. With respect with their stoichiometric coefficients, everything is in a one-to-one ratio. So that's why we're just going to some to assume it's either like minus x times 1 or plus x times 1, blah 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 stuff.
You make a good teacher, Veronica, because you explain everything so well.
Well, thank you very much. And so henceforth, you sum all the columns. Um, so for E of HA, we would get 1.00 minus x, and then right here you would just simply get x for the hydronium concentration and for the conjugate base A minus, and then now since you are given your Ka here, and you now found your equilibrium concentration expressions, you just basically plug in your values and solve for x. So for me, I'm just going to go straight forward and I'm going to go back to text if it's easier for you guys.
No, it's fine.
No,
I think
no,
you're doing
this is
great.
good. Yep, I think
So
you're doing great.
thank you. So So for here, you would set it up as 1.8 times 10 to the power of -5 equals x squared over 1.00 minus x. Now, one thing for me, I can be able to make the x is small approximation because of two criteria. From your Ka, the Ka value here has to be has to be smaller than 10 to the power of, of, of a -4. For me, 1.8 times 10 to the power of a -5 is pretty small, and also the ratio between your given equilibrium constant value divided by the initial. Let me bring the cursor. Divided by the.
Initial
Can
concentration.
everybody see my cursor?
Yeah, I can see it.
Yes, divided by the initial concentration should be like a less than 10 to the power of a negative 3 or 0.001. As for this value divided by 1, it is also smaller than well smaller than 1/1000.
Yeah,
So for
I
me,
usually like
I'm going.
generally the rule that I usually the rule that I pass on to students, I just say, yeah, if it's 10 to the negative fifth or smaller, you can always make the minus the small value of x approximation. If it's 10 to the negative third or above, you almost always have to do the quadratic equation.
Quadratic,
But
yes.
if it's 10 to the negative fourth, yeah, then that's a question mark. Sometimes you do, sometimes you don't have to do the quadratic. But that's where you have to be a little bit. You have to be a little bit circumspect.
I got you. Okay.
And just to be on
And
the safe side, it's probably best to, depending on, you know, if the multiple choice answers, how close they're, when you reach the order of magnitude 10 to the minus 4, I would say just go ahead and use it. Don't do a simplifying assumption,
yeah,
just to be on the safe side.
it gets a little bit risky
Hairy.
by
It
then.
gets hairy. It gets a bit
Yeah.
hairy. It may or may not work.
Uh, 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 um, I can check the uh, uh, I can check and make sure if the approximation is valid by like dividing x with the initial concentration times
Hmm.
100%. If your error is about uh, uh, is greater than or equal to 5%, it is not valid. You'll have
Hmm.
to solve it as a quadratic equation. For me, because I am a little bit lazy, I'm going to go ahead and take a little risk with the x to small approximation. So for me, sorry, I'm gonna go back to text. What I would get is I would calculate x by finding the square root, the, the square root of, of, of just basically 1.8 times 10 to the power of a negative 5 because that times 1.00 is just the same value. I can't do square root like on text, so I just like specify it via text. And for that, I got, and for that value, I got x equals, my, my keyboard is testing me. I got
I
x equals
I get 4.2 times 10 to the minus 3 molar. Is that what you get?
yes, same here as well.
Okay.
Now that times 100% is about point 42% error. Since it is a less than 5%, I can go ahead and and and
Use
and
it.
assume that
Agree.
the uh, approximation is valid. Yes.
Yes.
So so for the equilibrium concentration of the hydronium ion, as well as the conjugate base, because they are the same. This, sorry, I'm typing out the formulas. Because they are the same, I've set it up as set it up like this. Just give me a minute. Like this. If you can see my tiny text. And then
Yes.
as for the concentration of HA, it is going to be vastly different because it's going to be 1.00 minus the very small value of 4.2 times 10 to the power of negative 3 for molars,
So
which
it'll
what
end up
I
giving
got.
you a rounded value, which is basically 1.00, which appropriates it.
Yeah, basically.
Yes.
Yeah.
Yes.
back up to 1.00 molars.
Yeah.
Which in a way also proves my but
So your
what
assumption was valid, yeah.
yeah it it gives quantitative proof, so to speak.
Yeah. Excellent.
Yes.
Excellent. Well done. Very well explained.
Thank you.
Yes.
All right, so let's dive into the next one. Let's see what we got here. Hmm. So so a solution is prepared by dissolving 90 milliliters of 5 molar hydrochloric acid, 30 milliliters of 8 molar hydrochloric acid, and water is added to a final volume of 1 liter. Find the pH.
Let's see.
Oh, may I specify something real quick?
Yeah, by
Yes.
all
Um,
means.
uh, um, uh, I have to. Excuse me. We're actually not required to deal with scenarios with mixtures of strong acids.
Let's skip.
Okay.
Yeah, we can skip. I'm sorry.
No problem. No problem. All right, so a solution contains 1 molar HCN and 5 molar HNO2. Find the pH and equilibrium concentration of that mixture of weak acids one. That would be one I don't think she would have to deal with either.
Yeah,
Oh,
That would
okay.
that would be
quite
also
general.
yeah, that would be also a relatively tricky one as well. Um,
Yes.
let's see. I'll skip that one. That's something you might see in analytical chemistry.
Okay.
All right, so that brings us to the end, which um,
Yes.
if I want to
Mm,
tap into that practice, and I do have the answer key. No, I don't have the answer. Were there any questions from the acid-base workshop outline that I did? So that was
Um,
let me go ahead. I'll share it with you so you can see it. You probably already have it, but
yes, I have a
yeah,
question
yeah.
regarding number two.
Hmm.
Okay, so for me, I was able to find the products for these acid-base reactions. However, though, I wasn't able to figure out predicting where the equilibrium lies
Oh,
on the
okay.
left
That's
or right side.
this is So this is based on the principle that equilibrium always lies on the side of the weaker species. Okay.
Oh, okay.
So what you do is let me go ahead and open it up. Where's my acid base thing? I know I saved it somewhere. Hmm. Oh,
Okay. I haven't heard of this. Thank you.
I know. I know. I'm salty. I don't know why it did not download that to me. Download it. Yeah. Okay. It says it's here, and then it doesn't like. Okay. Am I just not seeing it? Here. Let me look. Look again. Uh. Oh, here we go. Okay. Yeah. I'm just blind. Sorry. I'm gonna pop it into the old workshop files. Do, 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 do. Yeah. Yeah. Yeah, there we go. Boom. Boom. Convert. Convert. There we go. All right. So, can you see the screen?
Yes.
Yes.
All right, cool. So basically, if you recognize which one's the acid, which one's the base, which one's the proton donor, which one's the proton acceptor. You can kind of proceed from there. Usually it's pretty obvious which one is which. Oh, whoops. That's not right. Let me try that again. NH3. And water. Now, the key thing here is you don't have to actually compare both. You don't have to compare the acid on the product side to the acid on the reactant side, and the base on the product side and the base on the reactant side. You only have to compare one, okay? Because the weaker acid and the weaker base will always be on the same side. Let me repeat that. The weaker acid and the weaker base will always be on the same side. So
Okay.
if I'm looking at this, compare the bases, okay? So what's the base on the reactant side for part A?
The hydroxide ion.
And what's the base on the product side?
Based on the product side, ammonia.
So if we're comparing hydroxide to ammonia, which one's the stronger base?
Hydroxide to ammonia. Let's see. I need to look at this table real quick. The base hydroxide and ammonia is what you're saying?
Yeah.
I'm
Now, in
pretty
fairness, you actually shouldn't need a table for this one.
Oh, sorry. I'm pretty sure it is ammonia.
Actually, it's hydroxide. Hydroxide's hydroxide's a strong base, right?
Oh wait, did you say strong base?
Yeah. Hydroxide's a
Oh, I'm
strong.
sorry. I was thinking of weak base. I'm sorry. I
Oh,
misheard you.
Okay. Yeah, sorry.
Forget
Yeah, hydroxide's a strong base, whereas NH3 is a weak base. So
weak
hydroxide,
base.
yeah, NH3 is definitely the weaker of the two bases.
Okay.
And then
You said
if you
strong base. Oopsies.
oh, whoops, no, that's sorry. Now, of course, if you compare water and ammonium, NH4, the water, of course, is going to be the weaker of the two acids. But yeah, the weaker acid and the weaker base are always on the same side. So once you've found one, you found both. So yeah, equilibrium will favor the side that has the weaker species. So this definitely favors products. What about the next one?
Yeah, and again, I want to repeat it because I don't think we can repeat it enough times. I mean, I think Victoria gets it, but the equilibrium is always going to lie on the side of the weaker acid and the weaker base. Why is that? Because when you look on the reactant side, you have a strong acid and strong base that's driving the reaction to the products. And so your equilibrium constant is going to be mostly products. It's going to be high on the numerator side and low on the denominator side.
And that basically just comes down to the fact that stronger acids and stronger bases are unstable, which is why they're strong. They're unstable, so they affect change. And the weaker species are more stable, so they're more able to just calmly stay where they're at. Does that make sense?
Good. Yes, good explanation.
They'll find that in a lot of these mechanisms, especially with organic chemistry, this notion of stability and of the weaker acid and weaker base actually comes up quite a lot. So that's a good thing.
It's an important concept to understand. Correct.
Do you want to take a shot at say C? A little challenging one.
Let's see. C. Sure. Sorry, that was my email.
No worries.
Okay, so for me, I'm looking at the. I apologize. Like I was like just taught of this concept.
No worries.
So the weaker species, weaker acid, and weaker base represents. Okay. So in terms of like acids, for example, I am comparing the hydronium ion and the acetic acid. I'm going to assume that the weaker acid is the acetic acid.
Oh yeah,
So
definitely.
and so
Hydronium has roughly an equilibrium constant of about 1, whereas like an acid dissociation, Ka constant of about 1, whereas
okay.
the HC2H3O2 has a acid dissociation constant of roughly 10 to the negative fifth.
Yeah, very small. And so since the acetic acid is on the product side, I'm going to assume that K favors products for B.
Okay. All right, what about
Is
C
that
then?
correct?
That's correct.
Oh, okay. As for C, I'm going to compare the bases. For example, the bicarbonate ion and the was this someone's kid?
That's my little
Oh,
girl.
oh,
Oh, she sounds
that's
adorable.
Gianna. That's precious Gianna.
Gianna. That, that, that's a pretty name.
Oh, thank you.
Sorry, I got distracted. Okay, so, oh, so comparing.
This is kind of tricky.
Okay, this took me a second.
Yes, this is kind of tricky.
Hmm, um, the bicarbonate ion acts as an acid on the reactant side of and then there's the hydrofluoric acid. They're
And
both weak.
well, let's see. Hydrofluoric acid, is that a strong acid or a weak acid?
That's a weak acid.
No, it's
Hydrofluoric
going to be
acid,
weak.
yeah. So
Okay.
you could do one of two things. You could compare the Kas of
That's what I
HCO3
was thinking.
Kas of HCO3 minus with the Ka of HF, because those are the two acids. Or you could compare the KBs of F minus and CO3 2 minus. It's up to you. It might be easier to find the values of the Kas for HF and HCO3 minus.
Yeah, we're going to have to like find those Ka values. They
Yeah,
are conjugate acids, and they are not like specified within the books. So for me,
I would say roughly about 10 to the negative 11th is the HCO3, and 10 to the negative fourth is roughly, I mean, it's going to be some number in front of that, but those are going to be roughly the values for the,
The orders of magnitude, yes.
yeah. So
okay.
equilibrium in this case is going to lie to which side?
Oh, it's gonna lie to the reactants
Yeah,
because you have a smaller Ka value.
exactly. Yeah,
So
yes.
henceforth K is going to favor reactants.
Yes.
Yeah, definitely, heavily.
Okay.
That's good.
And even if for example we didn't want to look at the values of the equilibrium constant, once we identify one of the species, hydrofluoric acid, as being weak, we can assume that the other weak species is going to be next to it, and so then the drive is going to be to the other side. So either or. Good job.
Yeah, so yeah, this is definitely the weaker of the two. And so yeah, both the weakest species of each type are going to be on the same side. So if HCO3 minus is the weaker acid, then F minus must be the weaker base. There you go. Well
Oh,
done.
let's see. Did I get that wrong? Hold on. I guess I'm confused.
Yeah,
Okay,
you
10.
had a little backwards, but you were saying the right concept, but I,
Ah, yes, yes,
she put
yes,
the
yes.
W by HF, and you assumed that she meant that was the weaker of the species.
Yes, yes. Thank you. Thank you for the correction. Thank you
Yeah,
for
no
rectifying.
problem. So yeah, so this is That's pretty much it. And there's, I mean, obviously there's a few other different practice problems of various different types that you could definitely try. I want to try and
Oops.
work on putting together the what should we call it, the answer key for this and posting it on the website. But basically, yeah, there, uh, you have the right idea, and I think you're going to be good going forward with this.
Oh,
Yes.
It
thank you
looks like
very
we're
much.
Yeah, no problem. It looks like we're just about out of time. Otherwise, I might do a few more problems, but I think we've covered a good amount. I think we've hit the different topics pretty well. So yeah, I
Yes.
think I think we're probably good to go. Well,
Yes.
uh,
Thank,
yeah, thank you so
thank
much
you.
for coming, and we will see you next week.